Thank you for the introduction. I guess my talk is the last thing that's separating us from the reception, so I'll try to keep it relatively high level. I won't try to go into details and will refer to the paper. This work was led by the New Jersey Institute of Technology Cybersecurity Research Center, which is an active and growing research center. And we extensively collaborate with DARPA, IARPA, defense industry, startups. A major research area of our center is lattice-based cryptography, which is a form of post-quantum cryptography. And all our research is centered around a Palisade library. So Palisade library is a publicly available library that incorporates different both fundamental blocks and cryptographic protocols based on lattice cryptography. It started from the DARPA PROCEED program, focusing on fully homomorphic encryption, and now we're extending it by the work that's being done for the DARPA SafeWare program. The library currently includes several major homomorphic encryption schemes, such as BFV, BGV, and can be used not just for program obfuscation that's discussed here, but can be used for protocols such as proxy encryption, for example. So this, our implementation partners and collaborators are MIT, Vinod Vaikunth-Nathan, UCSD Daniela Michancho, Worcester Polytech, and a couple of other universities. And we work closely with Raytheon BBN, with IBM Research, Shai Halevi, with Duality Technologies, and several other companies. So the library is distributed using BSD2 license. It's a cross-platform. It supports Linux, Windows, so has cross-platform support. The work that I discuss in this talk it was supported by the DARPA SafeWare program. It's actually still being supported by the DARPA program. It started in 2015, and essentially it's a sequel of work, of the DARPA PROCEED work, which gave us several homomorphic encryption schemes that gave us some new results in multi-party computations. So that particular program dealt with encrypting the data and performing computations on it. The DARPA SafeWare program deals with encrypting the computations, and, well, the data may stay in the clear. And the goal of this program is to build practical cryptographic program obfuscation capabilities that would serve Department of Defense needs. And when I say cryptographic program obfuscation, the idea is that these are the protocols that are based either on standard assumptions or assumptions that are close to standard assumptions versus the heuristic approach that have been used in the industry for many decades. And some of the security models that are explored as part of the DARPA SafeWare program, including distinguishability obfuscation, virtual black box approach, token-based obfuscation, and some other techniques that were discussed today, for example. So the motivating applications for the DARPA SafeWare programs are linear classifiers, for instance, for automatic target recognition systems, nonlinear classifiers, linear and nonlinear filters in signal processing, such as correlation filters, for example, supervisory control and data acquisition control systems. The particular problem that we tackled in this work is related to linear classifiers, and specifically we work with something that's called a conjunction pattern. And where this can be used, one of the possible applications is image recognition. If we wanted to determine if basically the certain image is close enough to a certain pattern, and certain features are extracted and then they're compared. And the security goal of this is we perform this obfuscation, then this obfuscated program, or classifier in this case, is distributed and can be used, and it's supposed to be secure. So the particular solution that we discussed in the paper in detail includes the 3 standard steps of any obfuscation protocol. So the first step is key generation, which of course includes some setup of parameters, the initial setting of parameters. and obfuscation. So the key generation and obfuscation are considered the offline stages. So certain keys are generated, and then those keys are used to obfuscate, to produce an obfuscated program. And then that obfuscated program is sent somewhere where it can be used for executions, thinking of it as a black box. Then the online stage, you load the program, for example, in the memory, and perform an evaluation. And the result of the evaluation should be the same as if you work with the program in the clear. The main idea is to make sure that no information can be derived from the obfuscated program in addition to what you would learn by input-output analysis, by feeding certain inputs and getting outputs. Conjunction obfuscation that is discussed in the paper, you can think of it as a sequence of bits with wildcards. And the use of wildcards allows us to support multiple accepting states. So if we think of it of this conjunction problem as a finite state machine, so multiple accepting states are supported, which is more complex than the traditional point function obfuscation where there is a single accepting state. And the wildcard is what creates the possibilities for different paths. The state transitions in this model are encoded as special types of matrices. In our case, those are matrices of ring elements, so matrices of polynomials. And then there is a certain process to load those matrices when the program is executed. So there is certainly an expansion that is involved in representing these individual state transitions as matrices. So the end result is if the certain pattern matches, then it returns 1, otherwise it returns a non-match. So to illustrate the idea of how those matrices are encoded, so for each possible bit in the pattern, for each possible state transition, we generate those matrices using trapdoor functions, so lattice trapdoor functions. And then afterwards, we feed a certain input, like in this case 1, 0, 0, just a 3-bit pattern, with a very small program for simplicity. And then specific matrices are selected from the program. And then we use a technique that's based on multilinear maps. So in this particular case, GGH15 directed encoding approach to perform the evaluation using those random matrices. And in this case, we compute 2 products. And then these 2 products are used to produce the final result. And the final evaluation uses the public key. During the obfuscation protocol, we obviously use the private key, so we use the trapdoors. The security model of this particular conjunction obfuscation protocol is based on so-called distributional virtual black box approach. So in other words, you cannot learn anything more than from the input-output analysis with additional requirement of distributional analysis. In this particular case, the assumption that was used was not a pure standard assumption, such as learning with errors, but it was a certain variant which at this moment is still believed to be secure, entropic ring learning with errors assumption. And the attack models that we actually discuss in the paper that can be used to break this are based on 2 approaches. So the first approach is based on on performing exhaustive search of inputs and outputs and trying to learn the pattern in this case through that analysis. And this particular approach essentially does not care which obfuscation protocol was used to produce this. We're just using the definition of virtual black box. And the second attack model is based on solving lattice problems in this case. So we have the matrices of ring elements, and then we try to solve a certain number of lattice problems to come to the solution. Sometimes you can combine those two techniques. So the work factor in this case depends on the number of wild cards that are allowed in the conjunction pattern. And the goal of this analysis is to find the minimum work factor for both the virtual black box model, a distributed virtual black box model, and lattice attacks. This is where we started. So our very first prototype, which basically was interpolated to a 32-bit pattern, something that could be considered more useful, had the following metrics. So key generation time would take 3 years. This is an estimate based on the 3-bit pattern that we had that we presented to DARPA in the initial PI meeting. Then the key size would have to be 15 petabytes. So this is where we were at the beginning of 2016, just to give you an idea. Then the program size would have to be 600 terabytes. The obfuscation time would be 70 hours, and evaluation time would be 9 hours. And this is for a 32-bit pattern. So obviously, this was far away from being practical. So by September of 2017, so a year and a half later, a little bit more than that, we were able to significantly reduce all those metrics. Specifically, key generation time and key size became a non-issue as compared to the original design. We were able to reduce the program size to roughly 6 gigabytes, the obfuscation time to 6.2 minutes, and again, the obfuscation time is something that can be considered an offline operation, and the evaluation time, which is the online operation, went down to 32 milliseconds. So 32 milliseconds versus 9 hours. So we had several orders of magnitude improvements in various parameters. And most of our paper discusses how we got to that point, how we were able to improve the original construction. And a lot of our optimizations were around the lattice trapdoor constructions and the lattice trapdoor pre-image sampling. So lattice trapdoors are a more advanced primitive, cryptographic primitive that are used for many protocols, not just program obfuscation, as we'll discuss briefly. And prior to this, there was no relatively efficient algorithm, especially for so-called prime moduli. So in this case, we used a construction that's based on ring learning with errors. We extended the classical binary gadget matrix approach from base 2 to base 2 to the power of 20. We improved the trapdoor pre-image sampling based on the collaboration with Daniele Michanchio's team, and we were able to improve both subroutines that are used in the pre-image sampling for lattices. And these particular optimizations have a broader impact than just the conjunction obfuscation problem that we were trying to solve. In particular, we applied this to the GPV signature and significantly improved the results for it, so that's a separate paper. We applied it to identity-based encryption. We applied it to ciphertext policy and key policy attribute-based encryption. The trapdoor sampling is used in predicate encryption and functional encryption, so a lot of advanced constructions that are based on lattices use lattice trapdoors, and a large number of optimizations dealt with this part. Then there were other optimizations that are more specific to the conjunction obfuscation multilinear maps. So for instance, we saw that in the original pattern, we worked with bits. So we considered a larger alphabet. So we found through some analysis that using a byte would be more efficient. So then we tightened the correctness constraints significantly by using central limit theorem and some other techniques. We improved matrix arithmetic. We improved polynomial arithmetic and used the so-called double Chinese remainder theorem representation in this case, which made it more efficient so we could work with native data types. We improved the integer sampling, Gaussian sampling that's used for lattices. We applied parallelization at multiple levels. And we also made a lot of improvements in the Palisade library itself, so more of software optimizations. So but most of our paper discusses those optimizations, how exactly they were developed. And I would refer to the paper for those details, or I would be happy to explain them offline during the reception. So one of the problems I want to discuss is how performance of the conjunction obfuscation scales with the increase in the length of the program. So we can get results comparable to 32-bit patterns for 40-bit patterns. As we can see here, the expansion is not significant. As soon as we go to a larger program size, for example, 64-bit program size, assuming 16 wildcards in this case, the program size is about 1 terabyte. So essentially, we're getting into the area where it may not be practical. And we were not able to run the 128-bit pattern because of the limitations of the systems we worked with. So there is still room for improvement. And a lot of the practicality questions that are being studied now, because this work is based on what we had in September of 2017. So how to efficiently implement more complex functions. In particular, we're looking at generalized branching programs and to see how those can be implemented. Is it possible to build general purpose obfuscation constructions that cannot be broken? Another aspect that was not discussed in this paper is that a lot of multilinear map constructions were broken in a general case, and that's still an open theoretical challenge to have a secure construction in the case of indistinguishability obfuscation. Are there other major algorithmic improvements that can reduce the obfuscation program size requirements? For instance, we saw that almost 1 terabyte is needed for a 64-bit program. And the other branch, and actually multiple branches that we're exploring now, is to look at other models. For instance, one of the issues we saw is related to the exhaustive search, with the limitation of the virtual black box model, because you can learn a lot through input-output analysis. So some other techniques, such as interactive token-based obfuscation, that limit the number of queries you can run against a program, are being studied now. This is the end of my talk. Any questions? Thank you.
Any questions? One question. There's one question.
Yeah. Hi, Pratik from Berkeley. So recently there's been work on doing this kind of obfuscation for compute and compare programs with LWE. Would you have an estimate of like the performance of your implementation on those? Have you guys even looked at it yet?
So you're referring to the theoretical work so we have looked at that, and the construction is very similar, but it's a generalization of that construction. Mm-hmm. And we actually consider that as a possible approach that we would want to implement. It is based on learning with errors rather than entropic learning with errors. Our initial analysis showed that it would be significantly less efficient than the construction that we have, and we're exploring slightly different approaches that are essentially related to token-based obfuscation. So constraint hiding, constraint PRF approaches, we're finding them more practical.
Okay. And another question. So I think for this you have to assume that the conjunction itself has some entropy. So like how much entropy is there in like these 32-bit patterns that you are obfuscating?
Yeah, so that's a very good question, and there is certainly a limitation in the assumption that this conjunction pattern has to basically have certain level of entropy. So it's a combination of two. There are two actual issues. So one issue is how many wildcard characters we have, and then for the rest we should assume a certain level, basically, of entropy. To To give you an honest answer, I would consider this more as a toy model at this time, and going to a model that hides, for instance, the fact that you're using conjunction pattern, which is what we're exploring right now with some branching program techniques, would be a better approach. So I'll go that far and just say it's probably would be more practical to work on those. And that's our next step, and we're working on that right now.
Okay, cool work.
Thank you.
Okay, let's thank the speaker again.